Hey everyone, welcome back. We're going to be doing our lecture on resistance training program considerations. When we are developing a resistance training program, it's important to consider the exercise type. So thinking through, is it dynamic or static? And with dynamic, what type of movements are we doing? A concentric, eccentric contraction? Are we fast on the concentric, slow on the eccentric? And when thinking about the eccentric contraction specifically, know that that actually helps to maximize strength gains more so than our concentric contractions. So if you've ever been in an exercise program or working with a coach or in group exercise, they might do a concentric contraction followed by a slow eccentric contraction. And the reasoning there is that research shows that it helps to maximize strength gains. The exercise order is also important. We want to start with our large muscle groups before moving on to our small muscle groups. We would do multi-joint exercises before single joint exercises, and then our high intensity exercises before our low intensity exercises. Obviously, a warm-up is important here, getting our body ready, followed by a cool down as well. And then with rest periods, this depends on the athlete client's experience with exercise and resistance training. For a novice, we would do 2 to 3 minutes of rest between sets. With advanced, we do 1 to 2 minutes between sets. And now time is a consideration. And so if we find that the client does not have enough time, we would want to potentially do circuit training where maybe we're doing an upper body exercise followed by a lower body exercise, still giving that 2 to 3 minutes for the novice client between upper body activities. This table was actually taken from the American College of Sports Medicine guidelines for exercise testing and prescription, and it provides recommendations for resistance training programs for different training level experiences and for different goals. So you can see the training program for someone whose goal is around endurance is going to look really different than someone who has a goal around strength development. Additionally, what we see is that there are changes and differences between someone starting out and someone that is more advanced when it comes to the load, volume, velocity, and frequency of workouts. Now with static training, we have our isometric resistance exercises. And with this type of training, it really gained a lot of popularity in the mid-1950s as a result of a lot of research that was being done around this type of training in Germany. And these studies indicated that static resistance training caused a just tremendous amount of gains in strength, and that those gains exceeded the gains resulting from dynamic contraction training. And then there were other studies that were published after, and unfortunately, they were unable to reproduce the original study's results. And training programs based heavily on isometric contractions have generally fallen out of favor as a result of the research not being able to show these tremendous strength gains again. However, I will say that static contractions remain an important form of training, particularly for core stabilization, enhancing grip strength for our post-surgical rehabilitation when one limb is immobilized and therefore incapable of dynamic contractions. So static contractions facilitate recovery and reduce muscle atrophy and strength loss that could occur as a result of injury or other reasons. With our resistance training program considerations, we need to think about the type of training when it comes to free weights versus machines versus bands and so forth. So Thinking about the pros and cons of all of these, the free weights are going to recruit supporting and stabilizing muscles. They're better for advanced weightlifters who, have the experience, are not at risk of putting themselves in an unsafe environment. And with the free weights, the range of motion being less restricted than with machines, um, it's going to be that the muscle is limited by the weakest point in that range of motion. So our free weights maximally tax the weakest points in the range of motion and provide moderate resistance around the mid-range. With machines, we typically think of these as safer, easier, more stable, and therefore better for novice lifters. However, they limit recruitment of targeted muscle groups, and so they're going to less resemble our activities of daily living. So the gains in muscular fitness that we make with resistance training, we see after 3 to 6 months around 25 to 100% strength gain. And the early gains are due to more effective force production. So we have, neural gains that are occurring, usually in those first 4 to 6 weeks. And then following that, we're going to see changes in our muscle physiology. So we're going to see structural remodeling. We're going to see things like our testosterone and growth hormones acutely and then chronically changing as well, which influences muscular fitness. We see that young men experience the greatest absolute gains in strength. And we know that muscle is very plastic, and so we'll be able to adapt pretty quickly and then hold on to those changes as long as we are doing some type of activity. However, this does follow the use it or lose it, or the principle of reversibility, quite closely. So if you stop a resistance training program, you're going to see declines in hypertrophy, strength, muscular endurance, whatever that plan was for, within a few weeks. So thinking about hypertrophy versus atrophy, hypertrophy, we're going to see increase in muscle size, increase in muscle strength. With larger muscles, that means we have more myosin and actin cross bridges, which allows for more force development. With atrophy, it's the opposite, right? We have a decrease in muscle size, a decrease in muscle strength as a result. And that, as a result, is really because we have less myosin actin cross bridges, allowing for force development. And as I mentioned earlier, we have strength gains as a result of enhanced neural control or muscle physiology, like changes in our muscle size, as talking about here. Okay, so when thinking about muscle hypertrophy, you may have all gone to the gym, and after an acute bout of activity, of resistance training specifically, you might have experienced that your muscles feel and look a little bit bigger. And that probably is transient hypertrophy. So after an acute bout of exercise, we have fluid accumulation in our interstitial and intercellular space. And as a result, we're going to see and feel that our muscles are bigger. However, this will disappear within a few hours. Now, over time, we will experience chronic hypertrophy if we're following a resistance training program for a few weeks. And this is going to reflect actual structural changes in the muscle. So we see things like an increase in our muscle fiber size, where this is resulting from protein synthesis exceeding protein breakdown. And we have hormones and other factors to thank for that. And then hyperplasia is thought to be an increase in muscle fiber number. And this has not been shown readily in humans. Although it's really challenging to prove hyperplasia in humans, it has been shown in other animal models. But specifically, the reason for that is that in order to understand if hyperplasia is occurring, you would have to take out a muscle bundle, count the fibers, put it back into the body, go through an exercise training bout, and then take that same bundle out, count the number of fibers. And yes, you could do something similar with like that area, but at that point, it's not as accurate. It's an estimate. And you don't necessarily know, are you getting a bigger size fiber? Are there just were there just more fibers in that bundle for some reason? So it's hard to prove. Okay, now when we think about how hypertrophy occurs, one of the things we look to are satellite cells. So hypertrophy is mediated by the activity of satellite cells, and these are thought of as myogenic stem cells. And these cells become active when we have a sufficient mechanical stimulus that is imposed on the skeletal muscle. And as they become activated, what they do is that there's going to be satellite cell proliferation. They're going to fuse to existing cells to create new myofibers. They promote protein synthesis over protein breakdown. And they're also really important in the repair of muscle tissue that needs to occur after an activity bout. Some more specifics around satellite cells is that they're going to facilitate muscle hypertrophy by donating extra nuclei of two muscle fibers, which increases the capacity to synthesize new contractile proteins. They do retain the ability to provide a pool of myonuclei to support muscle growth. And given that muscles are comprised of multiple myonuclear domains, hypertrophy could conceivably occur as a result of either an increase in the number of domains, which satellite cells are helping with, or an increase in the size of existing domains. And both are thought to occur in hypertrophy with a significant contribution again from satellite cells. Hormones and cytokines play an important role in hypertrophy as well, serving as upstream regulators of anabolic processes. And elevated anabolic hormone concentrations increase the likelihood of receptor interactions, facilitating protein metabolism and subsequent muscle growth. Many hormones are also involved in satellite cell proliferation and differentiation, and perhaps also facilitate the binding of satellite cells to damaged fibers to aid in muscular repair. Different types of exercise have been shown to cause acute and, in some cases, chronic hormonal alterations that appear to play a role in mediating hypertrophy and the signaling systems that are important for hypertrophy and needed for hypertrophy. The three most common studied hormones when it comes to resistance training are IGF-1, or insulin-like growth factor, testosterone, and growth hormone. So insulin-like growth factor is often referred to as the most important human anabolic hormone, which might be news to you, but in the exercise physiology realm, it really is becoming a important factor and has many areas where it influences hypertrophy, even more so than testosterone and growth hormone. It is thought to provide a main anabolic response for the body as a whole and shows enhanced effects in response to things like mechanical loading. The structure of IGF-1 is a peptide hormone and has structural similarities to insulin. Its receptors are found in activated satellite cells, adult myofibers, and Schwann cells. And during exercise, muscles not only produce more systemic IGF-1 than the liver, but also use more circulating IGF-1. And the availability of this hormone for muscle is controlled by its binding proteins, which either stimulate or inhibit the effects of IGF-1 after binding to a specific binding protein. There are actually 3 distinct isoforms that have been identified. We have IGF-1EA, IGF-1EB, and then a splice variant, IGF-1EC. And although all 3 isoforms are expressed and we can find them in muscle tissue, only the IGF-1EC appears to be activated by mechanical signals like exercise, resistance training, and loading. And as a result of its response to this mechanical stimulation, IGF-1EC is called the mechanogrowth factor. There is still a lot of research being done to understand the mechanisms of IGF-1's mode of action. However, it's thought that the mechanostimulation causes IGF-1 gene to be spliced toward that mechanogrowth factor, which in turn then kickstarts muscle hypertrophy. And then within a day or so, the mechanogrowth factor goes back towards the systemic IGF-1 isoforms, so the EA and EB. And the level of IGF-1 then remain elevated in a muscle tissue for up to 72 hours post-exercise. Another reason this is an important hormone for hypertrophy is that it also activates L-type calcium channel gene expression, which results in an increased intracellular calcium concentration, which you all know is important for muscle contraction. And this leads to activation of multiple anabolic calcium-dependent pathways, which we will talk about. And these ultimately are important for hypertrophy. Testosterone, this is probably one that you have heard more about when it comes to hormones related to strength training. It's a cholesterol-derived hormone that has an anabolic effect on muscle tissue. In addition to its effects on muscle, testosterone also can interact with receptors on neurons and thereby increase the amount of neurotransmitters released. It can regenerate nerves and increase cell body size. In the blood, the majority of testosterone is bound to albumin or steroid hormone binding globulin, with the remaining like 2% circulating in an unbound state. And although only the unbound form is biologically active, we can have some of the testosterone bound to albumin loosely become outbound. So you can think of it a little bit more than 2%, but this unbound testosterone is important because it binds to androgen receptors of target tissues, which are located in the cell's cytoplasm, and this causes a conformational change that transports the testosterone to the cell nucleus where it interacts directly with chromosomal DNA. And the effects of testosterone on muscle are seen in the absence of exercise, where we see the greatest amount being produced by the testes. But its actions are magnified by mechanical loading, promoting anabolism, both by increasing the protein synthetic rate and inhibiting protein breakdown. Testosterone can also contribute to protein growth indirectly by stimulating the release of growth hormone. And with what we see with research is that resistance exercise can have an acute effect on testosterone secretion. And research has also shown significant correlations between training-induced elevations in testosterone and muscle cross-sectional area, suggesting that acute exercise-induced elevations in testosterone may play an important role in muscle hypertrophy. However, acute responses are limited in women and elderly folks. mitigating the hypertrophic potential in these populations. And then we have growth hormone. Growth hormone is a polypeptide hormone considered to have both anabolic and catabolic properties. Growth hormone acts by inducing fat metabolism toward mobilization of triglycerides and stimulating cellular uptake and incorporation of amino acids into various proteins, including muscle. Growth hormone is secreted by our anterior pituitary gland and released in a pulsatile fashion. The greatest non-exercise secretions of growth hormone are going to occur during sleep. Recent research, though, suggests that preferential release of multiple growth hormone isoforms with extended half-lives during exercise, allowing for sustained action on target tissues. In addition to exerting effects on muscle tissue, growth hormone also is involved in the regulation of immune function, extracellular fluid volume, bone modeling. We see just so many different roles for growth hormone. And if you look it up, it's like 400 plus, like 450 actions that growth hormone has. And its role is apparent in 84 different cell types. But related to resistance training, we see that growth hormone levels spike after performance of various types of exercise. And exercise-induced increase in growth hormone has been highly correlated with magnitude of type 1 and type 2 muscle fiber hypertrophy. And finally, growth hormone is believed to be involved in the training-induced increase of IGF-1. Okay, with hypertrophy, we also need to consider our myogenic pathways. So hypertrophy is really facilitated by several signaling pathways, whereby the effects of mechanostimulation are molecularly transduced to downstream targets that shift muscle protein balance to favor synthesis over breakdown. There are several primary anabolic signaling pathways that have been identified, including the AKT mammalian target of rapamycin, mitogen activated protein kinase, or MAPK, and calcium dependent pathways. So what we see with our AKT mammalian target of rapamycin pathway, it's believed to act as a master network regulating skeletal muscle growth. And AKT is considered a molecular upstream nodule point that is both an effector of anabolic signaling and a dominant inhibitor of catabolic signals. And when activated, AKT signals mTOR, which then exerts effects on various downstream targets that promote hypertrophy in muscle tissue. The mitogen activated protein kinase pathway is considered a master regulator of gene expression, as well as redox status and metabolism. When thinking about this pathway specific to exercise-induced skeletal muscle hypertrophy, it has been shown to link cellular stress with an adaptive response to myocytes, modulating growth and differentiation. And then the calcium-dependent pathways, we have various types, and many of which have been implicated in the regulation of muscle hypertrophy. The calcineurin or calcium-regulated phosphatase is believed to be particularly critical regulator in the calcium signaling cascade. And the calcineurin dependent signaling is linked to hypertrophy of all fiber types, and its inhibition has been shown to prevent muscle growth even in the presence of muscular overload. So even if we were continuing to overload our muscles, if that pathway was blocked for some reason, we would not see growth. And then our neural factors that are essential for strength gain. Really, what we see again, like I shared earlier, is in that first 4 to 6 weeks, the main contributor to our strength gain are those neural factors. And so we can have strength gain without hypertrophy and changes in our muscle physiology. Research also points to this when we have studied unilateral resistive exercise of a specific limb. What we see is that when we do this type of exercise, it will also result in training effects in the unexercised limb. And so there's this motor control thing going on where there's cross education occurring. With the neuromuscular adaptations, what's really occurring is that we have an increase in motor unit recruitment and neural drive, rate coding, so there's an increased frequency of neural discharge. Autogenic inhibition, we have silencing of our Golgi tendon organs, which typically will kind of keep us safe and potentially prevent movement. Reduce coactivation and altered structure of the neuromuscular junction. So thinking through these, we've seen with research that a transient increase in motor unit firing rate has occurred. And there's training-related increases in the rate of tension development have also been linked to increased probability of doublet firing in individual motor units. And getting back to the muscle recruitment based on getting back to our muscle physiology and thinking about our fiber types specifically, when we are thinking around an exercise training program, it's important to note that you actually are training all of your fiber types with resistance training. So you might be trying to move from type 1 to 2, but really what's going to occur is that you're going to recruit your type 1 fibers first, then move to your type 2A, and then your 2X. And so you do this for efficiency. It's going by following this order and kind of like do my type 1 fibers produce enough force for what this activity requires? And if not, then I'm going to recruit my type 2A. And if they don't, then I'll recruit my type 2X. That's going to allow for force optimization with energetic efficiency, because your type 1s, those are your endurance type fibers. They can keep going and going and going, right? But if you recruited your type 2X first, you might not be able to recruit them later on when needed. So the key point here is that our muscle force production, not speed of contraction, is going to dictate our recruitment. Going back to hypertrophy and changes in muscle physiology, some of the changes that we see are in our myofibrils, our actin and myosin filaments, our sarcoplasm, and connective tissue as well. And these changes will occur along with the changes in our myogenic pathways, our hormones, to allow for muscle hypertrophy. And really the key takeaway here is with all of these changes that are occurring, they are promoting protein synthesis over breakdown, and they need to have enough protein available, an amino acid pool available for them to carry out these changes. So thinking about training in general. We have a lot of people who are strength athletes who don't like doing aerobic training, and then vice versa, right? We have a lot of aerobic endurance athletes who don't do the amount of strength training that they should be doing. But really, aerobic training is important for strength athletes, and strength training, resistance training is important for aerobic athletes. So with aerobic training, some of the pros of aerobic training for strength athletes is that it increases blood flow, which will help speed up recovery process between sessions. It allows for improved and more efficient recovery and may increase functional activity between sessions, increasing mobility and increasing the ability to burn fuel. With core training, this is going to be important for all exercises. Sorry, this is going to be important for all types of exercise goals. So our strength training, our aerobic training. It increases the sensitivity of our muscle spindles, which permits a greater steady state of readiness for loading joints during movement and protecting the body from injury. And has many other benefits as well. But if you have done either strength training or aerobic training without core training, the probability of you having an injury that you might feel elsewhere, but stems from your core is highly likely. So incorporating core training into your exercise plan is really important. The other thing about core training is that our core musculature is mostly type 1 fibers. So think about it. You are constantly using your core throughout the entire day. And so they need to be endurance-based fibers. So these types of muscle fibers, as we know, respond really well to multiple sets, high reps. And so when you think about the core musculature, making sure that you're doing an endurance-based type or muscular endurance based program for those exercises. This here is actually looking at blood lactate concentration with the number of intervals for anaerobic 5x200, 5x400, sorry, and 5x800. And what we're seeing is that with the high intensity activity, the 5x200 at top speed, we are having greater blood lactate concentrations than the other types of training here. However, what I want to mention is the importance of strength training for this. And when it comes to the anaerobic, for the aerobic oxidative, we see the importance of strength training to maintain the level of activity and the blood lactate concentration, even with 15 seconds of rest, because that's going to be an important, strength training is going to be important for our muscle metabolism, which blood lactate falls into. When it goes to our anaerobic ATP-PCR pathway, what we're seeing is that aerobic training is going to be really important for these explosive movements. Obviously, strength training is important for power output, but the endurance training will bump up our lactate threshold, which will allow us to continue out those 5x200s at the same performance over time. What this slide here is showing is that the crossover between aerobic versus anaerobic, really, this is highly variable what you'll read in the literature, but I really like this study because it shows the percent of aerobic metabolism at a 200 and 400, and we think that crossover would be between 1 to 2 minutes at high intensity. And we see so there's a large increase there, and then a similar increase we're seeing where now we're relying between 400 and 800 on 66% on aerobic metabolism. And so again, is it somewhere it's occurring between the 200 and 400 or 400 to 800, which for many people could fall between that 1 to 2 minute range in either of those two areas. And so for people that are going to be doing exercises above that 1 to 2 minute threshold, you really need to focus on endurance training as well. And then strength training is important for aerobic exercise because it improves our anaerobic capacity. It helps, as I mentioned on that blood lactate slide that kept bumping back, but it actually can improve our ability to buffer lactate. It increases our movement economy, enhances our neuromuscular function. There's an increase in our 2A muscle fibers, which provide more power output, increases our peak velocity, and reduces our risk of injury. So thank you for sticking in there for 2 long lectures. If you have any questions, feel free to reach out.